Okay. All right. So last time we talked about the R and S configurations. So when we left over there, it was about this one. Okay. So this is 2 bromo butane here. So what you need to do is always try to look for the chiral center over here. This carbon will be potential chiral center to check. This carbon should have at least always 4 single bond, right? So that means they have a here and 2 R groups here and bromine. But also make sure you know there is hydrogen are hidden there. We don't normally show you the hydrogen on skeleton structure, so this is sort of something you need to look for first. And then now we can do prioritizing the groups on this chiral center. I mean, possibly the chiral center here. So this is 4 chiral center with 4 different groups here. Now we can prioritize this one by following the higher atomic number. If you look at the periodic table, get the higher and the atomic number will give you a higher priority, so we want. But the problem is these 2. We have 2 carbons over here, right? So in this case, what you need to do is try to find out what might be the neighboring elements to those 2 carbons here. So this is now a tie in atomic number. Then you need to just go further from there and see what elements are attached to that each carbon. So this is the hydrogen, hydrogen, and hydrogen. This will be hydrogen, hydrogen, and carbon. Okay. Carbon, hydrogen, hydrogen. And obviously this will have the lowest priority because this hydrogen is the lowest in the atomic number. But these 2, as you can see, this one is higher than this carbon or this around neighboring elements here. So this would take 2, this would take 3. Okay? So now we have all numbers for priority on those groups. All you need to do is try to do those. Okay? So if you're rotating following 1, 2, 3, if you're going clockwise, okay, to the right way, you can call this R configuration. So that means if you had this group, now you're putting in the back here. You can actually call this S because the way you look at this compound, you're always going to place your number 4, the least priority groups, from to the back. So here you was already heading back from this plane of the chalkboard here, but now it's in a wedge. Wedge means it's going actually up this side, front side. So you're actually going to look at it from the other view. So it's still going this way when you look at here, okay? But when this comes out, you have to look at it from here. So now actually it's going, it looks like going still clockwise, but you're looking at it from the other side, it's actually going the other. So one trick you can do is when you prioritize the groups, if your number 4 group is heading back, you don't have to change anything. Just follow that rotations, which is R. But it is actually still going clockwise, but your number 4 is sticking up front, not in the back. Now you can say that it was R, but you can change it to the S. This is one trick you can do. So even though you see this is rotating to the clockwise, it actually counterclockwise because you have to look at the other side when your number 4 group going forward. Okay, this is one trick. So this is what we left last time. Okay, does it make sense? Okay. So then maybe you can ask me about how about the whenever you have a group number 4 is on plane, what we need to do now? That's the problem. So we'll do the same. this one is higher in atomic number, so it'll be number 1. These two are both carbon, they're tied, but for same reason, there'll be carbon, hydrogen, 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 hydrogen. So it'll be this. This will be 2, because carbon is higher than hydrogen. 3 and 4. Okay? So now you're saying, oh, maybe in this case, what we need to do, because this number 4 group now not doesn't going back or front, but on plane. Okay? So in this case, it's kind of tricky. This might be trickiest one to find out which is if it's in R or S. You can try to. So if it's in the plane, it's literally on the plane. So number 4, hydrogen is right going up here, right? Okay. So imagine there is one vertical axis going up, like this is hydrogen, and this is once again chlorine is going forward here, going forward here, and this methyl groups, I mean not methyl group, but in this is our group going back like this. So chlorine going up, methyl group going back, and this is on the same plane too. This same plane. So there'll be 1, 2, 3 going on. See? 1, 2, 3. Okay? So it'll be 1, 2, 3. And you once again you have to grab it toward yourself. So it goes what? 1, 2, 3. You see that right here? I'm grabbing the vertical X, which is hydrogen, going for 1, 2, 3. Imagine, right? You just put it up toward 2. So it'll be 1, 1, 2, 3, 1, 2, 3. Okay? Then it will be what? 1, 2, 3. Oh, so if you're watching from the video, it's the other way. So make sure it's maybe confused. But do it with your hand. It's vertical, 1, 2, 3. Put it up, 1, 2, 3. Then from my view, it's going clockwise. 1, 2, 3. So this will be I, 2 chloro, butane. Okay? So, yeah. This is a tricky one. But the main point is try to find the that number 4, the least priority group, on the axis and grab it and put it toward to yourself in the face, and just still count the same number. And if it's clockwise, it'll be R. If it's counterclockwise, it's S. Okay. Let's do one more. Whenever we to do one more. We good? So this is something you can just practice. Okay, so maybe it will take some time, but make sure just basically what you need to do, imagine those structure in 3D and see where you can actually look at those. Okay. All right. So let's move on to next part. So now you guys wonder why. Well, we care about the R and S structure of the isomers so much when we start talking of the stereoisomers. Which one of them was the enantiomer, we can call it enantiomer optical isomers. One good example is this one. So if you look at this one here, you have 2 chiral center. Okay, you have a 2 chiral center here, right? And then if you try to, let's change actually this. Here, if you look at this one over here, you have a 2 chiral center. Okay. So what you can do you see the 2 chiral center here and here? Do you see? Okay, good. So what you can do here, I will do the same. If you try to do prioritize this one here. There will be 1, 2, 3, and 4. Okay. Okay. So this will be going which way? Counterclockwise, right? So in this case, it's going to be S, right? But the as you can see, this is number 4. It's going forward, right? Okay. So like I mentioned before, if that is the case, change this one to R over here. So this is R conformation's chiral descent. Okay. So maybe I'll do the same thing over here. Okay. So it'll be 1, 2, 3, and 4. Okay. So this is also going counterclockwise, right? But once again, your number 4 group, the least priority group, going forward. So it'll be not S, but what? R. Okay. So in this case, this is the this is the 2 amino, 3 hydroxy, this 4 carbon butanoic acid because this is carboxylic group. In this case, we focus on the functional group, which is our suffix group. So this will be the most important part of your name. So you count the carbon from here: 1, 2, 3, 4. So this will be 2 and 3. So we're gonna call this 2R, 3R structure of 2 amino 3 hydroxybutanoic acid. Okay. So please keep this in your mind. Okay. So why we care about this one so much? If you try to draw the mirror image, right? It looks like this. Okay. Okay, so if you draw the mirror image to this one, which we know is 2R, 3R, okay, and then here it's going to be automatically. You don't even have to do the counting gold convention. It's literally just 2S, 3S. So you can try to remember whenever you do the R and S structure of the isomers, when you try to make an inertia, which is the optical, the mirror image of that compound, will have an opposite configuration of each chirality center. Okay? Does it make sense? So you don't even have to do it. Once you do this, you find that the R or S structure of the isomer, when you try to make a mirror image of that one, will be just literally opposite of each chirality center. If it was RR, it is going to be SS. So if it was so maybe you can change one. So we're changing this position right here. Put this one on this side. Okay, here. And then we'll just switch the position over here at the bottom. Okay. And now this will become 2R by 3S. But now can you guess what might be the conformation of these two? It will be still same. Oh no, sorry. So it will be 2R here, it will be 2S, but now it's 3S, so it will be 3R. Perfect. That's it. So this is the reason why we care about this one so much, because whenever you have they have an optical property. Did you guys watch the previous lecture when we talk about the optical property? So optical property simply means whenever polarized light, once again, you can watch the video again. Polarized light penetrating the sample, the polarized light will rotate. Okay, then it has optically active compounds. But these two rotate opposite direction but same degree. Okay, so maybe if this is degree to the right, this will to the left or right. So those were opposite are as conformation and also opposite in their optical property, exactly opposite. Okay, this is why the chemists start finding those enantiors and see what is the conformation of the isomers, which will show you also once again. If it's R in here, it should be S on the other side. If it's S here, it should be R on the other side. So forth. Okay, this is the only thing that I want to remember from enantiors when you talk about R and S in each chirality center. It makes kind of sense, right? You just need to do opposite in each image of between mirror. Okay. All right, so there's one thing I can say. Then now you're thinking, all right, so you have those two are the enantiors for sure. I got it. But how about this one? Okay. So those two are not opposite on only one side. So maybe these two are here, but this is opposite on carbon 2 chiral center. Here it has the same, but there's so you have the same chirality center on the carbon 2, but there's the other side is different. So it's slightly different by SR configuration wise. And then these two are opposite on both sides, so it's enantiomer, right? Or you can say enantiomer. I don't know who. Yeah, anyway, so then, but those two are in the relationship of diastereomers. So there's somewhat similar in one chiral center, but the other chiral center is different, opposite. Then if there are two positions that, so all chiral center are opposite on all carbons, there are two mirror image each other, means enantiomers. But there's only one chirality center is opposite in that compound. So you can see there's more than one chiral center. And in that case, we call this diastereomers. So maybe you can say, you can actually keep saying here, maybe this will be 2s, 3s, also 2s, 3s. This will be still 2, also diastereomers. They're same in only one chirality center, but opposite the other. So it doesn't matter. If you have a compound that has maybe 3 or 4 chirality center, but there's one or a few chirality center shows the opposite configurations, you can call that diastereomers. But they're all different. They're all opposite on each chirality center. We call them enantiomer. Okay, this is how we can adjust your reasoning. Okay, kind of makes sense. Kind of makes sense. So I'll give you one more example. Okay, so I'll give you one more example. It's the okay. So this is will take some time. Okay. Just a second. Give me some time. Almost done. Okay, so whenever you look at, this is glass tunnel. Okay. So whenever you look at this one, obviously they have so many chirality center here, and we call this glass tunnel. Okay, glass tunnel here. Okay, so it has so many so many chirality center. But when you look at the coprostano. Those two are very similar to cholesterol structure anyway. Only difference is double bond here. So whenever you look at this one, they will show you same, but this one is now going up. So should I draw this again? But so for this one, they're all same. They're all same structure. Cholesterol, coprostano, they have all same structure, but this one heading forward. This hydrogen going forward. So cholesterol is going back. So that's what? Trans. Remember this? Spice. You remember this, right? Polycyclic trans. The let me draw this again. It's, right? Trans. Right? Remember this, right? Here? I'll do this one here. Anyway. So anyway, but here, coprostano is going forward. It's going forward. So it's like this one or this one. Okay? So obviously, this one has this part, this one has R, this one has S. But all chiral centers are the same. But this one is only part that so the difference configuration, which is here, and it would go back like this. Okay? So as you can see, whenever you have the configuration change, especially on the bridge side of the polycyclic compound, it shows the huge difference in what? Shape. So even one chirality center can change, dramatic change in the shape. Do you have any bio major here? Bio major? We all were, okay. So when you look at all this cholesterol driven like compounds and all familiar compounds in a body, the most important thing as all scientists is structure, the shape. Because those will determine which functional group or which part of the compound will indicate or involve in certain type of receptor ligand binding and so forth of the protein interactions and everything. That is all coming from, most importantly from functional groups, but also the structure, which is a huge difference with one chiral symmetry. So this is a bit more dramatic example. So this is still diastereomers for sure, because when you have a one chiral center, it's different. But in this extreme case, you have a special name for this special diastereomers, epimers. We call this epimer, just one chiral center among lots of chiral center, but different, but still very important to remember. So we call this special diastereomers, still diastereomers, but more especially epimers. Does it make sense? I hope that makes sense, but if you have a question, just stop by my office. But obviously, I think we can finish the chapter 5 today. Okay, I'll try. And then we'll do the review on when. Do you guys watch the lecture? I'll do the review on Wednesday and Friday. So there will be enough time for us to do actual practical problem solving, more like exam-like problems. Anyway, okay. All right. So a couple more things for chapter 5. That is the tartaric acid here. Okay. What is so special about this one is. My drawing may not be perfect. Sorry. Okay, so here's the thing. Maybe we can do this. And then one thing what you can do is you also see the two chiral center from here too, right? So maybe you can do is, this is obviously oxygen number 1, okay? This is carbon, carbon, carbon here, but this will be number 2 because the carbon has actually there are 3 O's, so OH. So this is prior to this carbon, so 2, 3, and 4. Okay. So once again, this is going to be 1, 2. I'm sorry, 1, 2, 3, right? S. Is this S? Is this S? No, why not?
It's going forward.
Because number 4 is going forward, right? So now it's actually perfect. That's great. You guys did really well. Okay, so I'll do the same here. So this, now you're looking at this chiral center here. So this is 1, and same, right? 2, 3. So actually going this way. So this is also, I think, R. Am I correct? Please answer me. No, right? Why? Same, right? Same. So B. So whenever you have this type of the compounds, you can still do the mirror image here. Okay. So we try to do mirror image. Is my drawing okay? Is it okay? Okay. All right. Okay. So you see that it's mirror image, right? You see this kind of, do the mirror image here. So obviously, you don't have to do much now. What is here is R over S. That's R over there. This is S, perfect. And this is R, perfect. Because it's mirror image. You just need to pick opposite the other conformation for each chiral center on mirror image. Okay, makes sense, right? Okay, so in this case, the funny thing is, these two cannot be enantiomers, even though it's a mirror image. Because if you flip this one 180 degree, they're same. Okay, so here's the exception. I told you at the beginning of the chapter 5, if you have a chirality center, and that means they have 4 different groups. When you draw the mirror image, for sure it's different compounds, but still not superimposable to each other. But this one, those ones are. So does it make sense? So this is a kind of exception I'm giving you. So this is those 2 chiral center. So you did a totally opposite on the mirror image. That's totally fine. But now you flip it, it's the same. Do you see it? If you flip this one, it goes this way, and they show the same groups. Right there. Flipped, right? You see it, right? So this is the exception. So whenever you have more than 1, so maybe 2 chirality center, but if you can do the symmetrical, if you can find the symmetrical plane, here is where? Here. Okay? Okay, right here. Right? So then, even though those 2 has 4 different groups, so they can be 2 chirality center, but still those 2 cannot be enantiomers because there is 1 symmetrical plane you can make on this compound. So this is the exception, right? This is the so this is the exception. So this is a compound that has chirality center, but still achiral. So it's not chiral compounds. Okay? It kind of exception. It's kind of weird, right? But even though they have a chirality center, because of the symmetrical plane you can insert in this compound, they're achiral. Okay? And also, so this is a kind of special compound. So we call this meso compound. It's not meso compound, it's meso compound. So the those 2 are, whenever you see the 2 chirality center, still, if you can make some symmetrical plane on that 2 chirality center, you can say, oh, this might be still not chiral compounds, but achiral, because they'll be our mesel compound. That means they still have the chirality centers, but they're not chiral compounds because they're symmetrical on certain plane. Okay? Kind of makes sense, right? Because they are pretty much the same. They're really the same. Okay? All right. So okay. I think we're on the right track. Okay. So we're almost done with the chapter 5. That's good. I thought I might running out of time, but you guys are doing really well so far. That's very good. All right. So if this makes sense. The rest of them is very simple. I'll just go over a few more, and we'll do quick chapter 6, and we'll read them. Okay. So the second last one in here is it's actually called racemate mixture. So this is the mixture of enantiomers. So like I said before, I'm not gonna make the very serious problem about this one, but this is the only thing you need to know for this one, because it's we'll cover this one later. But so like I said before, the enantiomers has optical active rights, but when these two are the kind of opposite optical properties, right? If it's rotating right, it will rotate the right. The left, and if it's left or the right, and so forth. Okay, it's either dextro rotatory or levo rotatory. They'll actually kind of on the same degree, but the opposite direction. So racemate mixture simply is just 50-50 of each enantiomers for the compounds. Then what? Can you guys imagine what happens? So the racemate mixture will actually show you almost optically inactive. Can you guys guess why? So this is the 50-50 R or S structure of the compounds. Like I said, they all do the same degree of rotation, but the opposite direction, right? But when you mix 50-50 together, when you shoot the light, what happens? No change. Optically inactive. But each ones are. But when you mix, they're inactive because they're rotating in the same degree but opposite direction. So they become optically inactive in mixture-wise. The enantiomers mixture, 50-50, they'll make this mixture optically inactive. This is all I want you to know. That's it. It kind of makes sense, right? Okay. I'll move on. Okay. That's all you need to know. The one thing you might want to know, it won't be on the exam for your understanding. Whenever you have a mixture R or either S, right, in this mixture, whenever they do the reactions, they tend to keep the same. So whenever they do mixture, right, certain chemical reaction, they still keep the same. And also, other compounds that with the S or R either way, they tend to keep the same R or S structure or isomers in those chemical reaction process. But you don't have to. So anyway, so I'll move on to the last part of the. It's very simple. Okay. So if you can look at this carbon over here, this is 2-butanone, right? This is a ketone group here, right? Carbonyl groups and RR, ketone. Anyway, so this is the 2-butanone, and whenever this one can easily change to those two. Okay. So this is not the chirality center yet because it only has 3 bondings here. So it will be more like not tetrahedral, but more it's like a trigonal planar. But now it has got 2 groups on the top. It makes this 2-butanol that has chirality center on the second part. Sorry. So we don't have a chirality center yet in this compound, but it's really easy to have chirality center on this carbon later with certain chemical reactions, and we call this pro-chirality of the compound. Well, pro-chirality center. So that is not still legitimate chirality center yet, but it can be easily turned into the point where you can see the chiroid center at the certain chemical reactions there, which is very common in the organic chemistry. So this is the last part of the chapter 5, and we're done. Okay, so only thing I want you to know about this one is what does prochiroid center means, or parachiroid means. It is not the legitimate chiroid center yet, but it can be later be a chiroid center in the compounds. That's what we mean by prochiroid. So it's not really chiroid, but yet that's potential. That's what. To be honest, there's certain more on at the end of chapter 5. It's about even inorganic elements can be a chiroid center, but you don't have to know. They could, but in reality, they don't really act as chiroid center direction. So that's pretty much it. So I'll just move on to chapter 6, and then the one I'm doing right now should be the only one you can consider to this member. So only very first part of chapter 6 will be covered in exam 1. So the first one is addition here, okay? And second one is elimination. Third one is substitution. The last one is rearrangement. Reactions, or you can say so addition is more like you have a ethylene groups here, which will cover soon, and alkene groups, okay, with some hydrobromic acid here. I will become so this would be a good example of addition, because you're adding this H and the hydrogen and bromine on the ethylene here. Okay. So the elimination is kind of the other way, as you can see. This is sort of a okay. So some chemical reaction, catalyst or some other thing, may pick up those two. So it will become ethylene. So as you can see, it's actually taking those two out. So it's definitely eliminations. It's kind of applicable with it on the first one, which we call addition. So it's sort of a different concept. The bit more, the different one is substitution. It's just substituting some. So okay, this methyl acetate here with water, they will form acetic acid here, and the methanol. Okay. Okay. It actually substituted each other. Okay. So this is literally substitution reactions. I don't have space for this one. Rearrangement. Okay, let's see. Okay, so we have some here, dihydroxy, what's it? Acetone phosphate. But we can also substitute some groups there. So they will keep this most part same. But we're gonna switch those two. Okay, so this will become So do you see those switched? This is a glyceraldehyde 3-phosphate, which is, you may saw this in the biology. So you see this, right? You rearrange the groups on the 2 different carbons. So the last one was rearrangement. And this is the only thing that I want you to know for exam 1 on chapter 6. And that's the end of the chapter 6. For the exam 1. We'll do later part of chapter 6 after exam 1. Okay? Does it all make sense, right? Just you adding those, limit those, or either substitute it. Oh, sorry, it's gone. And or you can rearrange the groups on each different carbon. All right, looks good. I think we're on the right track right now. So from Wednesday, I'll try to do the practical problems. Maybe you can have some helpful, more useful time for doing some practice on exam 1. Okay, sounds good. All right, thank you guys. Bye.